Yeah, so I feel like finally we're ready to talk about some cryptography again. We had 2 entire lectures just on codes. Um, and again, there's like a huge topic, so once you want to delve into it, um, obviously there's a lot to discover there. But at least by now we have the basics of, first of all, what a linear code is, and then second of all, how to encode, and how to create code doors, and some of the properties at least. And then last time we gave an idea at a high level of how the coding works. So now, yeah, we could keep talking about codes for a long while, but I think it's probably better to talk a little bit about crypto, and then we'll add some other things. So what I want to present here is the Michaelis crypto system, which is going to be substantially different from stuff that we've seen before. And it's the first example of something that is not really based on the traditional problems like discrete logarithms and factoring and stuff. So the idea is the following. This was proposed in 1978. Okay, and so it is quite an old crypto system as well. I mean, it's basically the same age as RSA, Diffie-Hellman, and all the other stuff. And we'll see in a minute exactly why. You could ask essentially like this was not as popular or as universal as, like, say, RSA was. So the idea of the crypto system is very simple, because we have linear codes. So we say have like linear code C, and that obviously comes with a decoding algorithm. But as always, we didn't see too many details about the decoding algorithms, but essentially, to perform the decoding algorithm, you need to have some knowledge about the code. And therefore, you can assume that the code admits a certain description. Let's call it like delta, that allows to decode. Okay, and this depends on what kind of code you're using. For example, with the Hamming codes that correct just one error, like you have to have the columns in a certain order of the parity check matrix and whatnot. With those BCH codes that we saw, like you have to have like certain elements that you know, because then you have to like solve an equation, right? Mm-hmm. And put an equation and stuff. So in general, depending on like whatever family of codes, because there are many, there is a certain description that allows to decode. But without the description, you don't know how to decode, right? Then you just basically back to square one. You just see if you get a received word, then you don't know what to do with it, okay? And so this is where the trapdoor comes in. If you hide the description, then only the guy with the actual description can decode, but everyone else is faced with a hard problem. Okay, so basically decoding a random code is hard, and it's actually NP hard. Okay, so it's not just hard, it's actually like NP hard. And keep in mind that this is more than what we can say for crypto systems like RSA or discrete logarithms. Okay, but we don't have an official proof of hardness in the NP sense, in the complexity theory sense. But we'll get back to this point in a little while. But the basic idea is, suppose now I want to like encrypt a message. What can I do? I can put it in a code word and then distort it intentionally with some noise. And then like only the guy with the decoding algorithm can recover the message because he's the only one that can correct the noise. Mm-hmm. Okay, so it's a very clever idea, and it's nice. It was always fascinating to me because like obviously it comes from a very different era. Like coding theory is like based on communications, and that's always the priority, and that's how it was intended to be used. But then we can actually take it and take advantage of it for cryptographic purposes. Okay, so the idea of the Michaelis crypto system is the following. The key generation, which is usually the interesting, the important part, does this. So you choose a class of codes, and then say choose a code C of the chosen type. And this is usually represented by a generator matrix, right? So you can just choose a generator matrix G that carries the description delta that allows you to decode, for example. And then you hide it, and you do something like this. You sample. Remember, there's two things that we saw that we can do to generator matrices. One is if you choose an invertible matrix, right? So this is going to be a k by n matrix, right? Where k is the dimension of the code, n is the length of the code. So if you choose a k by k invertible matrix, okay, this is a change of base, right? So this just gives you another generator matrix. And then what you can choose is also an n by n permutation matrix, and this brings you to an equivalent code. So in the end, it's kind of like, it's kind of the same code, and then you permute it, so it kind of is an equivalent code, but it's not going to be the same anymore. Okay? So what you do is you then just compute S times G times P. Let's call this like G prime. Okay? Now, G itself is the actual code that you're interested in and say allows you to decode. But if you do S times G times P, then this brings you to another code, to an equivalent one with a different generator matrix, and it's not recognizable anymore.
Right.
Okay, so that's going to be my public key. Okay. And I can say formally my private key is composed by the S and the P matrices, for example.
Okay.
Or you can say, oh, G is my private key as well. I mean, anyway, really the thing that matters is that what you're going to use to decrypt is that decoding algorithm, right? That's the key of all of it. Mm-hmm. Okay, so the basic idea is now this is the trapdoor I'm setting up. I start from a code that I know how to decode with a description that allows me to decode, and then I'll just hide it. I'll just scramble it to a code that looks random, right? Because the problem is,
right,
we will talk about it later, but decoding a random code, and by random I mean like what is a random code? You just choose a random matrix that defines a code. Any matrix defines a code, mm-hmm, right? So you choose a random matrix of the proper dimension and rank and stuff that gives you a code. So if you do that at random, with overwhelming probability, the code is not decodable, right? Because we've already seen that like for codes to be able to decodable, they have to have like very strong properties. Right. And of course, when you see like proper code in theory course, you realize, okay, they are like quite strongly structured. So if you just take a random matrix over the space, of course, this is with what's the probability of hitting something that is actually like in the proper form, right?
Yeah.
So, okay, so now you set up the code, and then the encryption process is quite intuitive at this point because you have this public code and this private code essentially. So when someone encrypts, it takes the public code. So your plain text goes into a message M. Right? So now we're going to encode, we're going to put this into a length k, like any proper message that needs to be encoded. And then you compute M times G prime. So this gives you a code word, right? Mm-hmm. And then you add some error. So how do you do this? You just sample E at random, which sometimes we indicate with this symbol, and that's a $sign. Okay, it's a very bad $sign. But this error cannot just be anything because otherwise you risk not being decodable. So it has to have, and this is the crucial part, a certain weight. So it is in fq to the n if there's a correct dimension, it's a length n. Remember the errors that, like the error is an error vector that we add on top, but has to have weight, say, less than a certain w. Okay, where w is what? Is exactly the correction capacity of the code. So say if we were using a Hamming code, then that would be 1. If we were using like other codes, then then they can decode up to a certain radius that we explored in theory.
Right.
And because you chose your code, you say, I'm going to use this type of code. Okay, so then based on n and k and the alphabet size and stuff, you know exactly what the decoding radius is. So you just sample your error in the subset of the error vector of the vectors of length n, and then you create your C, which is your ciphertext.
Yeah.
Okay, so this is very intuitive. So basically, what is your ciphertext? It's a noisy code word that corresponds to your message. Okay, and now the decoding algorithm. Sorry, the decryption algorithm. So I should be precise. This is encrypt, and this is decrypt. But in fact, in Michaelis, the crypto system, decrypt and decode is essentially the same thing because the decryption consists of decoding. But so you receive your ciphertext C, right? And this is now a code word in the code given by G prime with some errors on it, and you'd like to remove the errors. And so what you do is, first of all, you got the private key. So what you can do is you, for example, multiply this by P inverse. Because that takes care of the permutation part. So you come back to the original code, right? So there was M G prime plus E, right? We multiply by P inverse, and we get M S G P P inverse plus EP inverse, right? So you see we're going towards the original code.
Yeah.
And in fact what we get is MSG plus E prime. Now the trick, one of the tricks is EP inverse is another error vector with the same weight because it's just permutation.
Right.
So you can still correct it.
Yep.
Okay, so you don't have to actually recover E original. In fact, you don't need to recover any error. You just need to remove the error.
Right.
And as long as the weight is
the same
or below the threshold anyway, you can get rid of it. So this is harmless. You can remove the permutation. Now what do you do? So now at this point, you have a certain code word U in the code plus an error vector, but you don't know how to decode in the code if you have SG, right? Mm-hmm. So what you're really going to do is decode with respect to G, and you can imagine that this is like a M prime G plus E prime, right? Where M prime is MS.
Yeah.
And so what you can do is here you apply the decoding algorithm, and that will that'll spit you out M prime, mm-hmm. which is MS. And so at that point, you just multiply by S inverse, yep. And that gives you S. Okay? So we've used all the tools. First, we remove the permutation. Well, that's good because it gives me a noisy code word with a different error, but with the same weight. So now I can correct this code word. So we use the decoding algorithm. And then finally, we use the third tool, which is once I recover the actual message, then I just come back to what the plain text was. Okay? Yeah. And I'm the only one that can do this because I know PNS, and the decoding algorithm depends exactly on G. Mm-hmm. Okay? And so this is the idea of the Michaelis crypto system. Everyone else will just see the vector C, which is mg prime plus E, and that will look like a code word in the running code. And so they don't have any tools to decode that other than attacks that we will see later, right?
Mm-hmm.
So hopefully this makes sense. It's a very simple idea, but it's very clever.
Yeah.
And there's obviously a lot of things that we have to explore. First of all, what kind of codes? Bob McAleese was an engineer, computer scientist, mathematician. He was working at NASA for a long time, Jet Propulsion Lab. So he had like familiarity with a variety of tools. Of course, he chose to use this class of GOPA codes, which is kind of a curious choice. People today are still debating exactly why that was the original choice. GOPA codes were invented by Viktor Gopa. It was a Russian mathematician a few years earlier. And you know, back in the day, like in the 70s and stuff, the relations between the US and Russia were not exactly the nicest. And so it's kind of weird if there was something like underneath. And the official justification that he said in his paper is like, oh, this is like a large class of codes with a good decoding algorithm. But you know, that's not the only one. And actually the fun thing is that a lot of other codes can be used in this. I mean, when you look at the description here, all I really need is a code with a decoding algorithm. And of course I need the class to be large, because otherwise it's easy to, if there's like very few of them, it's easy to recover the secret one, right? But as long as there's many of them, then you're fine. But he actually chose this class, and this is still like secure choice. So we'll talk about security right next. But what are these codes essentially? So this I think is interesting because we didn't really see many examples of like actually how advanced these code designs are. We introduced BCH codes, which are kind of like a basic idea of like taking these powers and stuff. So basically what you can do is you can, from BCH codes, define Reed-Solomon codes, which are essentially BCH codes with length n equal to the size of the alphabet. So these are like query codes, where you take the length like equal to the maximum number. And then you can generalize these to generalize Reed-Solomon codes if you add some scaling factors on top of it and whatnot. And then you can take from generalized Reed-Solomon codes what is called alternate codes. And alternate codes are of an interesting nature because they are a type of what we call subcode. And what the subfield means is that they contain elements that only live in a specific subfield of the field. So imagine that you are building your code over like FQ, where Q is, for example, 2 to the m, right? So your code is like over F16 or F32 or some like big field of, in fact, bigger than that, F266 or something. Right. With binary characteristic.
Yep.
So all the code words would be vectors with elements from this field, which is not the same as from 0 to 16. Remember, they have that polynomial construction. It would be like alpha squared, blah, blah, blah. Mm-hmm. So for example, if you take F16, you have like all the elements up to like power 3, right? Because it's a degree 4 extension. But then, so inside, for example, inside F16, you have F4, you have F2, right? These are all subfields. So obviously, if you take F16 has 16 elements, but if you take just 0, 1, alpha squared, that gives you F4.
Yeah.
And if you just take 0, 1, that actually gives you F2. So those are all subfields. So now imagine that you take a code, right? And the idea is the same, like in mathematics for many things. Like, what is a subcode? Is a subset of the code that is still a code. Right? Like for a group, a subgroup, and so on. So a subcode is just a subset of the words that are still tied to each other. Mm-hmm. And one way you can do this is by choosing only words that belong in a certain subfield. So imagine you have this code with all these code words that are defined over all the entire field. Right. If you restrict your attention to the ones that are just binary, for example, there's a few of them, and the interesting thing, but also is intuitive, is that you you can take these words and they form a code themselves. It's a subcode. That kind of makes sense, right? Because the code is linear, so if you take like two binary code words and you sum them together, you're going to get another binary code word. You're not going to get something in the bigger field. Right? So if you just take, for example, a code defined over a large extension field, and then you take the code words only inside a specific subfield, that forms a subcode, and that is exactly what we call a subfield subcode.
Okay.
And so what are these alternate codes? They are a subfield subcode of the GRS, which are a generalized version of the Reed-Solomon, which are like a particular type of BCH. So, like people constructed this over the time. But alternate codes, there's like many different types, and COPPA codes are one type of alternate codes. In general, alternate codes have this interesting property that they can be described by a parity check matrix that looks like this. Y1, Yn, and then it has x1, y1, xn, yn, and then it's x1 squared y1, xn squared yn, all the way down to x1 to the r minus 1, y1, xn to the r minus 1, yn.
Can you just push that up a little bit?
Yeah. Okay, so basically for two sequences x1, xn, and y1, yn, we construct a matrix of this form, and this defines an alternate code, where each row contains the 0, first, second, all the way up to r. Remember, r is normally n minus k, so it's the number of rows in the parity check.
Yeah.
Right? So we get all the powers of x times this y. And so usually you can look at this as the matrix 1, 1, x1, xn, x1 squared, xn squared, and so on, times diagonal matrix y1, yn. Gives you this. This is normally what we call a Vandermonde matrix. You guys have been through a matrix theory before, right?
Yeah.
But you can see Vandermonde matrix. But anyway, what is a Vandermonde matrix? Each row contains the power of the previous one. Okay, so it's like 1, 1, 1, 1, gets everything to the 0, and then x1, x2, x3, xn, and then x1 squared, x2 squared, times the diagonal matrix. So they have a very recognizable shape, and because, so now, as usual, this is one parity check matrix of an alternate code. Then, of course, for each square matrix that we get on the left, you get another. So you have always many parity check matrices, but with this one, you can decode.
Right.
Okay. And so COPPA codes are defined. And I may need to use a different piece of paper. How are COPPA code defines? So algebraically, and this I think is interesting, I don't want to spend too many details on this, but essentially, a COPPA code is defined by a bunch of elements alpha 1, alpha n in the field, in say f q to the m, right? They are distinct. Okay, so you have a large field, and you take like n elements and n distinct elements in the fields, and then so this is called support, and then you choose a polynomial g for COPPA, such that g for alpha I is never 0. So these are not roots of the polynomial. And this is what we call the COPPA polynomial. Is what defines the code. And then, the code is, so the polynomial will have degree, say, L. And then that gives us an n minus L code. If I take the code words to be all the words C equal to C1, Cn, that are such that the sum of ci divided by x minus alpha I is congruent to 0 mod g of x. Okay? So that means C1 over x minus alpha 1 plus C2 over x minus alpha 2. So it's kind of like you're doing a product C1, C2, Cn with the vector 1 over x minus alpha 1, 1 over x minus alpha 2. And then this sum gives you 0. So it's kind of a way to define a parity check matrix, right?
Yeah.
Because it's like this word times this particular thing gives me 0. And so you can do the calculate. So basically, a GOPA code is defined by support and a choice of polynomial. And then, you know, what is nice is like you can define it algebraically this way, but then you can extrapolate a parity check matrix, which kind of boils down to something like this. It's going to be 1 over g of alpha 1, 1 over g of alpha n. And then you're going to have alpha 1 over g of alpha 1, alpha n over g of alpha n, and all the way down to alpha 1 to the L minus 1 over g of alpha 1, alpha 1 to the L minus alpha n to the L minus 1 over g of alpha n. Okay? That's because basically, like, you can extrapolate it from here, do some calculations. It's like a textbook exercise, and you just see, like, okay, that corresponds to evaluating the polynomial in all the elements of the support and blah, blah, blah. Okay? And, you know, in the end, this is going to be a matrix with elements in the field, right? Because g of alpha 1 is like an element in the field, and 1 over is just its inverse, right? And 1, so this is just going to be a matrix in the field with like elements in the field. Yeah. But it responds to this structure. And again, if you see this structure next to see this structure, you can see this is alternate, right? You can see this is alternate where like the y sequence that you're multiplying is the 1 over g of alpha I, right? And the x sequence is the alpha 1 alpha n that you take the powers of. So this is an alternate code. And so it comes with the decoding algorithm as well. And what do you need to decode? In this case, you need exactly the alpha 1 alpha n and the polynomial g. So if you take this and call it like delta or something like that, is your key to decoding. So that's what Michaelis does. It's basically like it takes this information and saves it as private key, and then it gives you like a G for this code that looks like completely random. So you don't know how to decode unless you have the alpha 1 alpha g. So you're not really hiding the G, you're hiding the H, but it's the same thing.
Right.
Okay. And so this is the idea of, and so then everything proceeds normal with the Michaelis cryptosystem. So you publish this G for the GOPA code. So one thing you could do, for example, is start from the GOPA code by selecting these elements forming H. Then you bring H to systematic form that gives you the systematic form. Then from the systematic form of H, you get systematic form of G, because remember it's just the other way around. And then you multiply by S, a random S and a random P, and voila, you have a random key, public key. Cool. And this is really kind of like what is done in practice.
Okay. Yeah.
Okay. Okay. So then this is the choice of GOPA codes, and then these codes can correct a certain number of errors. In particular, basically, what happens for GOPA codes is that the dimension is at least n minus ml, but L is the degree of the polynomial, and m is the extension degree of the field. And the minimum distance is usually L plus 1. But if you take the code to be binary, so if you take the subfield subcode, so if you take this over f2 to the m, and you take all the binary words, that's a GOPA code, and then the distance becomes 2L plus 1. So the binary version of these codes, so if you take binary GOPA codes that are defined with just the binary words out of this whole bunch, then the distance is quite high. It's 2L plus 1. But remember, L is the degree of your polynomial. So if it's 2L plus 1, then that means, but in this case, you can correct actually up to L errors. Right? Because remember, it's like distance minus 1 over 2. Yeah. So basically, this corrects as many errors as the degree of your GOPA polynomial. That you can take as big as you want. Essentially, normally you can take, for example, your code to be like length 2000, and then your Gopper polynomial is like 1000 or something like that, about half, rate 1/2.
Yeah.
Okay, so it corrects a decent. That's the dimension of the parity check matrix. The Gopper polynomial is not exactly that, but anyway, you can correct like a decent number of errors. Okay.
Okay.
So that's the first thing. Is we have the Maclise cryptosystem, and the idea is that we hide the code, and then we exploit the fact that we have a decoding algorithm that we are the only one that we know. And so there's actually two assumptions here when we talk about security. There's two assumptions. The first one is that this process, so the matrix G prime is indistinguishable from random. Okay. So basically, the scrambling process that you do is a strong scrambling process. This is not the only scrambling process there. This is the Maclise original idea. Maclise original idea is very simple. You take a code and you take an S and a P, and it brings you to like an equivalent code with a completely messed up generator matrix, and then you're not able to figure out. Okay. And you kind of need both the S and the P, because if you only say use the S, for example, then it's a generator matrix for the exact same code. And you can actually, for example, you can even recover the S. It's a K by K system, so you can just set up an algebraic system and solve it. But if you don't have the S, if you just have like a G and a GP, then it's also hard. It's also easy to recover the P, just the P if you have just the P. So you need both the S and the P. Okay? Because together they mess up the structure now. But again, if you have just the G and then the GP, then you're just moving columns around. It's easy to recognize.
Yeah.
So it's kind of like the same idea as what we were having, even at the very, very high level, when we have like a simple cipher. It's like, I'm just gonna permute things, or I'm just gonna do substitution. But if I do them together, it's like much harder. So this is kind of basically boiling down to what is called the code equivalence problem. It's finding this equivalence between the code. If you have a G and an SGP, find the S and the P. Right? And then the second one is the decoding hardness. And this is in fact not an assumption, but it's actually a well-known problem that we can reduce to. So if you take a random code with certain parameters, then it is hard to decode in general. Okay, and so this boils down to so let's go back here. So assumption one is basically the code equivalence problem, more or less anyway, which tells you that give you G and G prime equal SGP, find S and P. Okay? And so in this particular case, actually, it's not exactly the code equivalence problem, because you only see G prime. You don't see the G.
Right.
But in general, what people study is the code equivalence problem. So even if you are allowed to see the G and the G prime, you still shouldn't be able to tell what the transformation is.
Yep.
Okay. In the case of the Maclise cryptosystem, this is not good, because if you do see the G, then you're actually able to decode. But it's good to know that the problem is hard in general. Even if you were given the G, you still cannot find what the mapping is between the two. And so so if you are able to attack this, then it kind of leads to what they're called usually structural attacks. Okay, so attacks that basically take the G prime and try to recover the G from it. sort of total break attacks, right? It's kind of like taking n and trying to factor it.
Yeah.
You're really trying to break the key. And in many cases, these were actually successful. So what people have been trying to do, for example, after Michaelis' original proposal with GOPA codes, they were like, can we use other codes, right? And there is many classes of codes out there. Of course, again, I keep repeating this, but there's like, elliptic curves, elliptic codes, polar codes, concatenated codes, like a lot of, or why didn't we use like BCH codes or GRS codes in the first place? And people have tried and said, okay, let's do the Michaelis cryptosystem with other type of codes. It should work just the same, but in a lot of cases, the code was too easy to recognize. Okay. So if you take, for example, a BCH code, the structure is so strong that you can, like, again, set up like some system of equations and like figure out what the columns are, and then you're done. So obviously this comes with a computational cost, and I'm not going to go. So some of these attacks are actually quite clever, but basically in either polynomial time or a reasonable amount of time, you're able to like break the key. Mm-hmm. So binary GOPA codes are actually some of the few types of codes that. So there is this idea that like if the code is too good or too strong, something that you actually would use for communication, it's not secure for cryptographic purposes because it's too recognizable. So it has to be like some code that is like not actually too good.
Yeah.
Okay. Assumption 2, the decoding hardness. Basically, we can formulate the problem like this. Given linear code C and a word y in f q to the n, find x such that the distance between y and x is minimal, which is the same essentially as saying find x such that y is equal to x plus e, where e is a minimum distance, right? So y is any word in the space, and find a code word that corresponds to that y, okay? And this is usually called like the general decoding problem, or GDP. Yes, and this was actually proved to be NP-complete. And it's a good thing, right? And in fact, what was proved to be NP-complete is not exactly the general decoding problem, but is this other problem which is the complete equivalent, which is called SDP, which says, so this is general decoding, and SDP stands for syndrome decoding. And so what's the syndrome decoding problem is essentially the same thing, but instead of giving you a matrix G, suppose that I give you a parity check matrix H. Right? So in the GDP, given a code C, given a matrix G, find the error. Here I'm giving you a parity check matrix H, and then a vector S in F Q to the n minus k, and fix an integer W, which is the target weight. Find vector E of weight W such that H times E is equal to S. Okay, so given parity check matrix for a code, again, can be the same code as the other one, and given a target syndrome, find the error that gives me that syndrome. And you can see that these two problems are like essentially one and the same. For example, if you have the GDP problem, what you can do is build a parity check matrix and compute the syndrome of Y, and the syndrome of Y will be exactly the syndrome of E, right? Yeah. Because X is a code word. So then if you're able to solve SDP, you can also solve GDP. right? Because suppose you have a solver for SDP, you give a parity check and a syndrome, spits out the error.
Yeah.
Well, then if you're given a noisy code word, what you can do is take the parity check, compute the syndrome, apply the solver for SDP, bang, you're done. So this is a reduction from like one to the other. You can also reduce from the other to the, so if you have a SDP instance, you can transform it into a GDP instance. So the two problems are really equivalent. And so SDP was proven to be NP complete, and therefore the GDP was also proven to be NP complete. Because NP complete problems, they are equivalent to each other, right?
Right.
So the good thing is that this problem basically is like as hard as any other problem in the NP class. That's what NP complete means. So it's a very hard problem. Now, so Maclise doesn't use SDP, it uses GDP, because it does give you a noisy code word. Okay. This, of course, strongly depends on the weight. It depends on the fact that the weight is actually kind of low, because if the weight is too high, then it becomes easy. But as long as the weight is below a certain bound, which is called GV bound, as long as the weight is below this GV bound, is usually the problem is considered hard and the solution is unique. So that's exactly what we want for our crypto system. Now, of course, one thing that is interesting is that it's possible to turn, because these two problems are like actually one and the same, and we already know that essentially the G and the H are kind of dual of each other, then we can kind of imagine to turn Maclise into like a dual version, and this is what Niederreiter does. So I'm going to go here. So there is this crypto system by Niederreiter, which is from 1985, if I'm not wrong, and is usually considered like a dual of Maclise. And let's see what it looks like and why is the case. So the Kijang does this. It selects H to take a code C. It can be the same GOPA code as the other one or whatever. But you're going to choose H and then hide it as HP. So in the same way, for example. Yes?
Okay.
Now, so instead of using a generator matrix, you use the parity check. Now to encrypt, so I'm sparing details because it's the same, like sample a random, take a parity check, sample a random invertible matrix S, blah, 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 send them a random permutation, blah, blah. Now to encrypt, you want to use the syndrome. So what you're going to do is you're going to put your message not in the code word, but in the syndrome. So you're going to put this into your error vector.
Okay.
Of weight, say, less or equal W. Okay? So this already looks a little bit more finicky because before you have your message, you just have like certain number of bits of messages, you just put it into this code word. But now you actually have to transform, you have to have like some clever encoding scheme that maps bit strings of a certain length, which is your message that you want, your plain text, into strings of fixed weight with just a certain number of non-zero elements.
Right.
So it's kind of a little bit more annoying. People have been thinking about this for a long time. You use some computation time to do this. It's not so practical as the other one, but in the end, this is not as much of a problem in modern day for reasons that we'll explore later. Okay. So now, okay. So that's your message. So your ciphertext is not going to be a noisy code word now, but it's going to be H times Z transpose.
Right.
Okay. And then the decryption, this is kind of similar to what Maclise did. You have your code word, which is H times Z transposed. And now what you're going to do is first you're going to multiply by S inverse, which gives you, sorry, I guess this is H prime, the public one. Okay, so that is S inverse SHP E transpose. And so then there's a change of base. So wait, now you have this is usable. And so this really looks like H times a vector E prime transpose, where E prime is PE. Right?
Okay, yeah.
Makes sense?
Yep.
And again, this doesn't change its weight, so H is usable, and then from this, you're just gonna apply your decode, and this will spit out E prime. Well, and then you just apply the inverse to it and recover it. So you kind of do the same as in McLeese, but in the opposite order. First, in McLeese, you have to remove the permutation, then that allowed you to do the decoding, and then you remove the S. And then here, you first remove the S, so it brings you the correct code. And then but again, you interpret the vector. So yeah, it's because before you were looking for the code word, and now you're looking for the vector. So that's why you do it in the opposite order.
Right.
And the crucial property is always that, like, basically permutations don't change the Hamming weight, so you can recover the other vector, or in the case of McLeese, remove the other vector, and then like you're done. So you see that it's kind of a dual version of McLeese because it uses parity check instead of generator, and instead of putting your information into the message, you put it into the error.
Yeah.
In a sense. Of course, one big difference is what the McLeese crypto system is probabilistic, because part of the encryption process is sample an error vector. After, when you are done and you decrypt, you can throw away the error because it contains no information.
Right.
Although it is interesting to note that you're actually able to recover the error. So if you wanted to use it and put something in it, or then you, for example, you can use it to check. And this is what people do for like advanced security levels. Because in certain crypto system, when you decrypt, your randomness is lost. Whereas in McLeese, when you decrypt, you're actually able to even recover the randomness that was used. And that means that, for example, if you want to check that your decryption process worked correctly, you can just kind of like re-encrypt, right? You can just like, oh, this is the message, this is the error that my decryption algorithm gave me. Let's check that it's exactly the ciphertext that I received. And you just like resum them together, and it should work, right? So McLeese is randomized, but the randomness is not lost during decryption. But it is still a probabilistic crypto system, and that means, remember that we've seen some. We've seen, for example, the Goldwasser-Mikali or El-Gamal, right? That means that every time you encrypt even the same message, you're sampling like a random error vector, and in principle, you're going to get a different ciphertext.
Right.
That is good because it gives you intuitively much more protection against even basic attacks.
Yeah.
Okay. Now, so whereas the linear crypto system is deterministic. Because your message goes right into an error vector and there's nothing you sample. So every time you encrypt, you're going to get the same thing. So obviously, for example, this one is not secure against like distinguishing attacks, right? Because it's just deterministic, so you can just encrypt. It's like RSA. You just encrypt it twice and whatever. Okay, but so it's considered like the dual, in the sense that like it's nice to think that this is the dual because the parity check defines the dual code and blah blah blah, and because it's based on the problem. So this is based exactly on SDP, because the problem given a ciphertext, recover the plain text is exactly solving SDP.
Yeah.
Right.
Yeah.
But it is substantially different in other regards compared to McLeese crypto system. For example, it's deterministic versus McLeese that is probabilistic, right, randomized. The nice thing about this, also compared to stuff like RSA, is that basically, provided that assumption one holds, that the code actually looks like random, then the one-way CPA security is based exactly on these problems. Okay, so there is no gap, because remember, for example, in RSA you have like, okay, there is the factoring problem, then there's like computing the E-root problem, and then there's all these like problems that are potentially easier.
Right.
And similar for like the El-Gamal is like, it's not actually based on this logarithm, it's based on the Diffie-Hellman problem, which is potentially easier than DLP. Whereas here, this is actually based on an NP-complete problem.
Yep.
with the caveat that you have to assume so that your scrambling matrix is good enough. So if you assume that your matrix is indistinguishable, then even from a formal point of view, your one-way security is exactly an NP-complete problem, not something potentially easier like ad hoc. Okay? So the hardness of the assumption 1 is something that, again, depends on the code that is used, and is not something that we're going to go much more detail on, because it requires, like, obviously an extensive knowledge of how these codes are built. But instead, it's easier to analyze what we can do with respect to like a random code. Okay, and this is the next thing that we're gonna do. Is that making sense up to now?
Yeah.
Okay. Okay, so basically, let's focus on the part 2, which is the decoding hardness. So suppose that my scrambling method is good enough, I choose a code that is secure, and I cannot, given this matrix G prime or H prime, I cannot recover where it comes from. So it looks like a completely random code to me. What do I do if I'm given like a random code word? Obviously, not anything that is practical, because otherwise there would be no point in coding theory anyway, right? So the whole idea of coding theory is like I have good code, and with this I can decode better. Otherwise, basically I can brute force, right?
Right.
So, okay, so what are the attacks on this? The first would be brute force, for example. Now, of course, if you have like W errors, and N is the length, forget about the error values, actually, because we're talking about query codes, right? Codes that are defined over F4, F16, or FQ, or any Q. So the actual position, so the Hamming weight tells you that there's like non-zero positions, but you still actually have to find also like what the error values are. But then, you know, basically once you find the positions, finding the error values is just like checking a few possibilities. So that's not the most important part. The important part is really finding what the error positions are. So let's assume that the code is, I'm just looking for the error positions, not the values. So basically this is what you do for binary codes. Binary codes, you just have zeros and ones, and all you do is look for the error positions. Then if the code is not binary, you also have to do like another step to figure out what the value of that position is. But again, you can do it pretty quickly because at that point you know which columns to sum, so it's just a matter of figuring out what the errors are.
Yeah.
Okay? But even if I was just finding, try to find an error vector of weight W and length N, then obviously I have N choose W of them, right? And this number is, of course, huge.
Yeah.
As soon as N is like a few hundred and W is like a few dozen, okay, and this explodes pretty quickly. So this is, it can be approximated exactly, but clearly this is not practical if you're just doing a search, like a brute force search, okay? So, but like with everything, like with all the crypto systems, this means that you cannot choose your parameters to be trivial, like because if they are too small, then obviously like one could just look for the error vector. If you can just like search them all, then you try them all, and then it works. Okay, so at the very least, that binomial right there needs to be big enough so that you cannot just search. Okay. Now, of course, like with all the other crypto systems that we saw, we can do better than a search. That would be like looking for primes like one at a time.
Right.
Obviously, we know we can do better than that. And so actually this all falls in a category that we call information set decoding, or simply ISD, which started in like 1962, give or take, and is still going strong to this day. Because like similar to what happened for like, say, prime factorization algorithms, right? People have been asking these questions for a long number of years, and then when these things start to get used, there's more pressure and more relevance to these things being found, and there's an acceleration. So people were doing the sieve of Eratosthenes since the Greeks,
Yeah.
basically. And factorization algorithms have been known for centuries. But then, like in the latest years, that's where all like the complicated like number field sieve and stuff came out, because we wanted like really to push to the limit of like how efficient we can factor, because that is now relevant
Right.
to cryptography. And same things here. Ever since codes were introduced, we're like, okay, what happens if I try to decode without any information on the code at like a relaxed level? But then when it became relevant, then people were like, okay, can we push it? And in the latest year, there have been something like 25 different research papers just on ISD pushing the complexity down by a little bit at a time.
Yeah.
Oh, I can do this trick, it increases, this trick, it increases. Okay, so it's a very similar. It's a very, as you can imagine, common process, right?
Yeah.
And so the basic idea of information set decoding is very intuitive. It's interesting, and I think it's important to understand. Suppose that I have a generator matrix G. Okay.
Okay.
And in practice, so here's what happens. If G is in systematic form, then it's in the form IK M, whatever, right? Where IK is the identity matrix. So when you see a code word, right? A code word is C equal M times G. Well, then M times this thing, the first K positions will be exactly the ones of the message. So your code will be like M1, MK, plus other positions that are redundant, but these are exactly the information symbols.
Mm-hmm.
Okay? So if you use a matrix in systematic form, then basically you can see your message right in the first K positions, and then like you have all the redundancy part later.
Yeah.
Cool.
Yeah.
Now, so this is important. Why? Because okay, now my matrix is not going to be in my generator matrix that you got in Macris or something, is not going to be in standard form, right?
Mm-hmm.
But you can still kind of try to find something like this. So in particular, what you can try to find is you can try to find a set I of columns, say I1, IK, right?
Uh-huh.
Yeah, there is a subset of the set of columns,
Okay.
and call GI the matrix, which is a submatrix of G of just columns I1, IK. Okay, so you take your matrix and then you just select just those matrices indexed by those.
Mm-hmm.
You form a K by K matrix,
Mm-hmm.
right? So you have like all the columns, and just like the first, the third, and the seventh, right? And then you just like take that submatrix. Well then, if GI is invertible, is square, right? This is square.
Mm-hmm.
So if this is invertible, then what happens is that G prime equal GI inverse times G, right? Is another generator matrix for the same code.
Yeah.
Because we said that you form other generator matrices by multiplying with matrices S that are invertible. Well, GI inverse is such an invertible matrix,
Mm-hmm.
and it gives me another generator for the same code. So it's another generator basically as G. But the difference is that now this one, this matrix here, you see GI inverse, if I consider, you have to kind of visualize it, but like when you multiply GI inverse with G, the columns in the positions indexed by I will go to identity.
Yeah.
We go to 1, 1, 1, and zeros everywhere. So that will put that submatrix into identity. So it's kind of like, by doing this process, you're kind of doing a standard form, but not in the first K, in like the first, third, and seventh.
Yeah.
Okay? So if you choose these columns here to be the first K columns, then this process gives you exactly a systematic form.
Yes.
Now if you choose these columns to be another subset of columns, doing this process gets you a systematic form,
Right.
but not in the first K positions,
Mm-hmm.
but like distributed on the columns, right? But essentially, every now and then you will have a column that the first I1 column will be 1, 0, 0, 0, 0, and then like the second one will be 0, 1, 0, 0, and so on. So you're kind of getting a systematic form, but not necessarily in the first k positions.
Right.
In the other word, you can think that basically you're taking a systematic form and you're applying a permutation to it, so that the columns get scrambled around. Okay. So now, what happens is, though, and the crucial point is, these columns will carry the information symbols in just the same way that the systematic form does, except they're not in the first k positions, but they're in the positions indexed by I. So such a set is in fact called the information set. Okay? So the standard form is, for a reason, the standard form, where the information set is the first k positions. But there are many information sets. Basically, every subset of columns that is invertible gives you an information set. And now you can maybe see where this is going. Because the idea is, if I have the information set, I can read exactly what the message positions are. Remember that my task is I'm given actually y that is mg plus e.
Right.
Okay. Actually, I think this we call c, and this let's call it something else like u or something. Okay. So I receive a code word with some error positions. Now, for example, suppose that I have no errors in my information set. Well, then I can immediately see which one the message is, and I have decoded.
Yes.
Okay, this is not likely to happen for the standard form. But if I try different information sets, eventually I may be able to find k columns, and then none of them carry an error, right?
Yep.
And then, boom, that's the coding there.
Yeah.
Okay? So I basically keep trying different information sets until I find one that contains no errors, and from that I say, okay, I can get the message from that.
Yeah.
Cool. So it's quite clever. So yeah, so suppose that I receive, so how does the algorithm actually work? Basically, not even in pseudocode, but like a very intuitive level. You receive C, you then select, so receive C, you then select an information set, say at random, right? And then suppose that there are no errors there, right? And so basically C and U are the same on those positions, right? That means that CI and UI are the same, essentially. And so then what you can do is you can just set U equal to CI times G prime, and you can obtain even the error vector as C minus U at that point. Okay. So now, of course, this suppose that it defines errors. The next step is obviously to iterate this. So you just keep choosing different information sets, aka you just choose like different permutations.
Right.
For example, you can imagine you take your matrix and you receive vector, you apply permutation, row reduce to get the standard form, right? That is the same as looking for an information set.
Yeah.
Except so it's easier to imagine, for example, that I do a permutation and then reduce because the Gaussian elimination does it in the first k position, so it's kind of weird to do it in like punctured positions like that. But yeah, basically that's what you do, right? So you receive a word, you choose an information set, and you compute like CI, and then GI, right? And then you calculate, let's say, C prime, which is C minus CIG, and you want to check. Now, of course, you don't know. So that's a crucial thing. You don't know. Like you check whether this thing contains errors or not, and then basically, if this is equal to a code word, then you know that it doesn't contain errors, right? But in fact, you can even do better than that. So one thing that we can do is, rather than looking for 0 errors in the information set, why don't we allow some errors in the information set and then we do a matching process similar to what we were doing with other types of algorithms. Remember that we saw for like collision algorithms. So for example, you can say allow p errors in the information set. And so rather than checking that basically that gives you syndrome 0, check that that corresponds to a certain amount of sums of rows. So what you can do is you can just choose, for example, a subset P, a P set A1, AP of the columns that you choose an information set. And then you can compute basically weighted sums of the type G hat equals sum xi GAI from 1 to P. So you sum some of the rows of G, and then see if you write E as C prime minus G hat, this should have weight W. If this works, you found the error vector. Right?
Okay.
Otherwise, you try a new, either a new subset of error positions, or you start over with a new information set. So this already improves on the basic idea, which is I choose an information set, I see if this thing gives me syndrome 0, which is a code word. If it does, I found the error vector, right? But then you have to like cycle over different information sets. Here, I'm not looking for 0 positions, 0 errors in the information set, and assuming that all the errors are out. I may have better luck by just like allowing a smaller number of, let's say I have 100 errors, I take 20 of them, and I suppose that I can allow up to 20 of them because it's easy for me to check sums of 20 rows, right? Yep. So you see where this is going. Like you take a small number, if you can sum and check quickly small sums of rows, and then that means that your search is going to have better luck. If that doesn't work in the end, you just start with an information set. So this is already a first kind of very intuitive variant that is due to Liam Brickell. And then you can like really push this to the extreme by allowing different number of errors into different positions of these like things that you're looking for birthday collisions and stuff like that. Right. So the next step is like, okay, now I'm allowing some ones into my information set. Now suppose that I'm also fixing some zeros outside the information set, so I know that there are no errors in there, and then like you can make lists that are smaller and smaller and like match them like 4 ways and stuff. And in the end, this can become quite complex. So for example, here is an excerpt. Basically, you can see what I'm talking about. In the plain ISD, I look for 0 error positions in my information set. All the errors are out. Right? These are the k columns that I'm choosing. These are the n minus k columns that I'm not choosing. Yeah. The Lee-Brickell like fixes some errors, and then the remaining errors are out. And then you have like more generalizations. So like, okay, suppose now, for example, I have p errors here, but instead of just looking for w minus p errors in the remaining, I fix also some zeros in some say L positions, and so now you have 2 parameters, the p and the L, that you can play with. And then this is further generalized by, instead of looking for p errors here, I say put p here and p here, and I split the information set in 2. I look for p errors here and p errors here, so that I can match these 2 lists. And then here it becomes w minus 2p here, and so on. You can like obviously like generalize and look here. They match this list here, but they also allow for like q and q here. So it gets more and more complex. And the result is that essentially all this algorithm, and this is what you should take away, all these algorithms have a complexity which is of this form. It's basically big O of 2 to the theta n, and basically it's a function of n and r only. Remember that r is defined as k over n, which is the code rate. Okay, and basically that makes sense because it only matters n, which is like how long the code is, right? And the rate, which is like how rectangular it is essentially. So commonly, for example, the rate is 1/2, which means that the dimension is like half of the length. Okay, and so yeah, so clearly it scales kind of proportionally to that with a certain, so it's exponential with a certain constant in front of n. Okay, and what you can see is that essentially what happened in research is this, where you have like certain variance. Oops. And you can see that what the research does is just push this exponent, which is like 0.057 to 0.055, and all the way down to like 0.049. But each of these is a different research paper with a different technique.
Yeah.
So at this point, we are not even like fine graining, we're beyond fine graining, right? We're like super tinkering with the thing, because these techniques, they look actually quite complex, and there's pages of calculations and theorems. They bring your exponent down by like at 0.06, actually 0.006, okay? And that is considered like a big improvement. Okay. Now, in practice, these are improvements. In some cases, they do bring to concrete speed-ups, and in some cases they don't.
Yeah.
And in some cases they do, but for example, they come with a price, right? So we've seen similar situations with both factoring and discrete logarithms. For example, in factoring, we have these improved sieving methods. They knock your exponent by a little bit, right? And sometimes they're worth it. In this case, what the problem is that for this to be really, really relevant, your n would be to be really, really big.
Yeah.
Because all these are asymptotic estimates, right? So if your n was like going to infinity, then this would be like a really, really big improvement. Now in practice, the code that you use is obviously not infinite length. The length is like 100, 1,000, 10,000, whatever you want, right. But it's not asymptotic, and therefore these improvements are kind of like special because it's like, if someone could like knock in half the exponent, it would be a thing. But if you're just like taking a 0.006 out, then the improvement is maybe like a few complexity bits, which is still relevant, but basically instead of being 2 to the 80, you're like 2 to the 75, okay? And again, it's still relevant. You may have to change your parameters, increase your length a little bit, right? But in the end, they're not devastating, and they do not change the overall nature of this kind of attacks, which is exponential. Which again makes sense, because if it wasn't exponential, then we wouldn't be talking about coding theory in the first place. Yeah. Right. And then the other thing is that we already saw, for example, that with discrete logarithms, there are some algorithms that require a lot of memory, like the BSGS, and some that don't. And so what happens here is that of course, some of these things require you to store like 4 different lists and then like look for matching, so that obviously the storage space goes up quite a lot. So you also may get to the point where you do get a time reduction, but your space complexity starts getting crazy, and then it's not worth it anymore. So what people use in practice is a blend of these techniques, right? Depending on the situation, how big n is, how big the storage comes out, and so. But what is interesting then, to summarize today, is this. We have a crypto system that is based on 2 pillars, right? That one comes before the other. The first one, you have to assume that your code is not recognizable. If that is not good, then the system is not secure. But provided that is true, then your public key looks like a completely random matrix that you don't know anything about. The best thing you can do is try to brute force decoding, which is, even with the refined techniques, essentially information decoding. And you're trying to solve obviously a problem that is NP complete, so it's hard. The best algorithm, it's got to be exponential or sub-exponential, and therefore what you can really use is use ISD as a tool to assess exactly how to select your complexity. Yeah. Okay. Similar to what people do with other, of course, crypto systems. Like, okay, I take RSA this many bits, and then it gives me like this much security. Here is the same tailoring process. You're like, now you have like this tool to play with. Your crypto system is going to use a certain NK code with a certain length and dimension up to correct a certain number of errors, depending on what type of code you're doing.
Yeah.
Well, you choose your N and K such that the ISD, the best ISD, brings you to say 2 to the 128 or something, right? You use that complexity estimate, and then you set your length, and then you can clearly see that some codes for the same length can correct more errors, so then ISD becomes harder and whatnot, and stuff like that.
Yeah.
Okay, so that is usually what the process is. As a food for thought for next time, we can look at obviously one very important feature of Michaelis, and it's the following. Is everything making sense? So, as we've done for the other crypto systems, I think we describe the system, and then we look at the underlying problems and its security.
Yeah.
And now we maybe want probably like next lecture talk a little bit more about the features and push it to the limit. Right? So one thing, of course, to keep in mind is that both in the Radar and in Michaelis, your public key is going to be a matrix like of this form. Yep. And so this is like, say, for example, in Michaelis, a K by N matrix. And of course, to have the minimum security that you want, we see like not only the brute force, the N choose W needs to be big enough, but even the ISD needs to be big enough. So the N cannot really be like 20 or something small like that, right? So this has to be, for example, Michaelis in the original manuscript, which is 1978, remember, selected N to be 1024. And then rate about 1/2, so K is 524. So then N minus K is exactly 500. You see like the rate is about 1/2, which is usually, usually is kind of like where the hardest instance, is around the 1/2, maybe 3/4 mark for the rate. Obviously, if the code is like very high rate, which is like very long with very few rows, it's very rectangular, then it's easier to recognize words.
Yeah.
Right? Okay. And also vice versa, if the rate is very low, not only is a bad code for communicating, but also it's like almost a square, so then it becomes easy to. So with this setting, a GOPA code can correct up to 50 errors, okay, which is a decent number. But of course, what it means is that this matrix is a 524 times 1024 binary matrix. So it's easy to count. These are just bits. It's 524 times 1024 bits. And in fact, this comes down to about this many bytes. Once you divide by 8, which is, say, 65 kilobytes or something like this. Okay, so it's clearly like a really big key. Yeah. Because compared to RSA, it uses 1024 bits for the modulus N, and this is what RSA is using right now. In the future, if you are crazy about security, you could use like RSA 2048 with 2048 bits. Right? Obviously, this is like much smaller than 65 kilobytes. That is a huge key. And so that also is the code that Michaelis proposed in 1978. This code right now carries about 2 to the 60 security bits. Okay. Which means that the cost of ISD kind of went down a little bit from what Michaelis expected, because of course there was a 1978 paper and ISD has been improved a lot since then. Yeah. So it's still secure, but like not to a very high level. So modern day Michaelis would need like much bigger code, well, a little bit bigger code anyway. It doesn't use 1024, I think it uses like 4,000 or 5,000, something like this. But then the key becomes even bigger. Yeah. And then so already this was historically a problem in 1978, because like, look, we have RSA, it works, it's so great, and then like this other system is neat, but the key is gigantic, so why would everyone think about using it, right? And so what people have been trying to do for a long time is trying to improve the system to like reduce the key size, make it fast, practical, and now this has become important, because what's going to happen is that soon we won't be able to use RSA anymore. So we do have to switch to other systems, and the difference is that we do have a quantum computed polynomial algorithm for solving factoring and other related problems like discrete logarithm, but we do not have explicit tools for solving something like random decoding.
Okay.
Okay, and so this is the first example of what we call a post-quantum crypto system, which essentially means that at least until now there is no known dedicated quantum algorithm that completely breaks it, like it does for RSA and discrete logarithm.
Yeah.
Okay? And yes, the quantum computers would bring us speed up in, for example, some of the search part that we do in the information set decoding thing, but it's not going to bring my problem to polynomial time.
Right.
And so, yeah, so now this kind of algorithm is even more relevant, and the research on this is even more relevant. This is what we are doing. And of course, the next lecture we can see a little bit more about this, and then we'll see other examples of post-quantum stuff. Okay?
Yeah.
Very, very cool. Cool. So let me stop this.